so it's time we can start our seminar, and today we have a guest, Professor Mario Ulrich, but he is not completely a guest. He's how to say, he's professor in the laboratory of I forget the name, the multidimensional approximation and application in Moscow University. So please, Mario.
So thank you very much. Let me just skip that. Okay, so today I will give a talk about, say, kind of survey talk. Some of these results I would already think are a bit older, some years, but I realized that actually it's not so old, and there are also some new things coming. So I think the main theme of the talk is information-based complexity. It is about approximation and integration, as it's already written here, but with a very special focus on high-dimensional problems. So let me give an introduction and what kind of problems are solved and not solved, and I think I will give about 7 or 8 open problems that I think are particularly in particular interesting. Okay, so what is the general problem we have? The problem is we have for a function f. By the way, do you see my mouse?
Yeah.
Can I move it? Okay. So we have a function which is defined on some d-dimensional domain, and during this talk I will focus on the cube mostly. I will only give some comments on general domains here, but often only the cube is considered anyhow. And what we want to approximate is maybe the integral of a function, so just the integral over the d, or we want to approximate the function itself, where an of f is an algorithm that uses n function values of f. But that's the general thing we want to do. And there is the emphasis here is on the dimension often. Okay, so what do we want? We have a class of functions, fd, not only one function, and we have maybe given an algorithm, and we want to understand the worst case error that you have. I think that's well known to the audience here, so maybe I don't have to say much about that. Just to fix notation, I use e int here to indicate that I'm considering the integration problem, still worst case error, or I write app here if I'm interested in the approximation. And for most of the talk, I will be only interested in L-infinity approximation. Clearly, one might consider many other problems here. So one might now ask, what is an algorithm and all this stuff? And there is a general theory, what we would consider an algorithm and what we would not consider. But let me just add maybe I can say directly now, that in the setting I'm considering, we only need to consider linear and non-adaptive algorithms. So by quite old result of Bachwalow and Smoljak, it's completely enough in the setting we are in to consider algorithms of this form. So we have function values, and these AI are, in the case of integration, just numbers, and in the case of approximation, are functions. Anyhow, it's enough to consider these kinds of algorithms as long as the set of functions we are interested in is symmetric and convex. And but this obviously might not hold for other problems. That's very specific to the integration and the L-infinity approximation setting. Okay, so what do we want? We want to find the best algorithm. So again, I'm writing int or app, depending if I'm interested in integration or approximation. So I want to know what is the minimal error that's achievable with n function values. So I consider the quantity from the last slide, the error, the worst case error of one algorithm, and then I'm taking the infimum over all what I consider algorithms. Okay, as I just said, it's enough to consider linear ones here. And what is the, I think, not core idea, but what is in information-based complexity, bounds we have are often better stated the information complexity, which is just a minimal number, minimal n, is needed such that the error is smaller than some epsilon. That's in the rest of the talk called n of epsilon and the class clearly that we have. Okay. So this is the quantity we want to study, and we want to have this quantity clearly not only upper bounds, we also want to have lower bounds because we want to know this guy. Okay. So what is the classification we use? What we are using is if this n epsilon, so the minimal number of function values, is upper bounded only by epsilon. So never forget d is the number of variables of our functions. So if this is actually independent of d, we call a problem strongly polynomial tractable. If this guy depends polynomially on d and also polynomial on 1 over epsilon, we call it polynomially tractable. And to also have some lower bounds, so some bad classification, we use the term curse of dimension, sometimes curse of dimensionality. There exists some constants such that information complexity is lower bounded by a constant times some 1 plus gamma to the d. For all epsilons.
May I ask a question, please?
Yes, sure.
So in your first line, you suppose that your class defined for all dimensions? How?
Yeah, yes. Oh, sorry.
So for all d, it's a sequence of classes.
Yes, I have a sequence of classes defined for every d. Yes, I will come. Maybe it's clear in the next example I'm presenting, but yes.
Okay.
So,
okay, thank you.
So let me start with some examples just to get a bit of a feeling. So a very simple example are the Lipschitz functions. And in this case, that's only the univariate. That's only the univariate case. So there is no d, and d will be on the next slide. So in the univariate case, so just all functions with Lipschitz constant 1, and we might want to compute the integral of or f itself, so also the approximation problem using n function values. And I think what's well known to the community is we even know the optimal points that we need for function evaluation, and they are just equidistant. Equidistant points at these positions here, compute the function values of f, and then for approximation, you just use the linear spline for approximation. And yeah, similarly, you can do for integration. And what you can almost trivially compute is that the worst case error in this class is for approximation 1 divided by 2n. This means n app, so the minimal number of function evaluations needed for approximation is given by 1 divided by 2 epsilon. So that's just to get a feeling what these guys mean. And similarly, you can do for integration, and here you get 1 divided by 4 epsilon. So these quantities are just precisely known. I think known since whatever, 80 years or so, maybe even older. So if you now come to the d-dimensional example, so you take all continuous functions in the unit cube, as we just heard, so we have fd is a whole class. For every d, we defined this class here. Now we take Lipschitz functions with respect to the supremum norm. As I said, only an example. And then it's known since the 70s that error for numerical integration in these classes, worst case error of these classes, is exactly d divided by 2d plus 2 times n to the minus 1 over d. That's just exact formula. What do we get from that? We get that if n is 2 to the d, you can just plug 2 to the d in here, and we see that we only reach an error of 1/2. Right? So sorry, here must be a 1. Okay. The sense is you can improve the error only by a factor of 1/2 by using 2 to the d function evaluations. And this is what we call the curse of dimension. This means this class is for any practical meanings just useless. Okay, that's not enough. If you want to have a very high dimensional problem and you really want to solve it on a computer, then this class is just too big because exponentially many function evaluations are just bad. Okay, there are many similar results by colleagues of S. Babenko, Sukharev, and Chanaya using different Lipschitz constants and so on and so forth. So there are quite a lot of results. Okay, so now where we know Lipschitz functions are not enough. So what could be a way out? So what can we try to change here to maybe get a better result? And I think one of the easiest ideas is we consider smooth functions. With smooth, I mean finite smoothness here. So let us consider these, say classical classes of functions. We just take unit ball of ck, which means I take all functions of k times differentiable functions on the unit cube, such that all partial derivatives are bounded by 1. One class here, together with this norm, that's the maximum of all these derivatives. And maybe we do not agree that partial derivatives are important, and we also, I don't agree in every case, so you might also consider all directional derivatives bounded. So here I consider d beta as the multilinear mapping. So they really do directional derivatives of order k at most. Okay, so for the rest of the next, say, 15 slides, just mind these notations. I use ckd for the class where all partial derivatives up to order k are bounded by 1-dimensional functions. And I use the c tilde k as the class where I'm bounding all directional derivatives up to a certain order. Okay. And again, there are many old results on this, and I think final solution to this problem was given by Bakhvalov in 59 to the integration problem, and Tikhomirov in the 60s for the approximation problem. And so it's known that there are some constants that do not depend on epsilon, only on the smoothness and the dimension, such that the number of function evaluations needed is approximately some constant divided by epsilon to the power d over k. I think that's well known. So we know that, stated differently, the order of convergence is k divided by d. Okay, so this is known, and the upper bounds here are achieved by product rules. So we just take if function evaluations on the full grid, d dimensions again. But here the problem was, for several years, that these constants were not quite well understood. But the behavior on the dimension was, I think it was decreasing with d in the lower bound and super exponentially large in d in the upper bound. So there was basically, it was not possible to gain precise knowledge in high dimensions here. This was changed in 2016 first, then we had some follow-up papers. And these letters here are Eike Hinrichs, Erich Nowak, myself, and Henryk Wozniakowski. And what we managed to prove is that for every fixed k, there exists constant that only depend on k, such that the error for numerical integration is bounded by these quantities here. You see, that only scales linearly in d here, at the order of convergence, n to the minus k over d, and then some factor d in the lower and in the upper bound. So what this shows is that the number of function evaluations needed is something like d divided by epsilon to the power d over k. Okay. So that's even worse than the curse of dimension. You really have something like d to the d over k in this case. So for every fixed k, for every fixed smoothness, you can take smoothness 10 to the 6, doesn't matter. If you consider a very high dimensional problem, then these guys explode. So this means also smoothness does not seem to be enough for having a problem that can practically be solved on a computer. So in this setting I'm talking about, so integration of these functions, and I'm considering the worst case scenario. Okay, so that I have some proof here, and since I think it's quite instructive, let me say some words about the proof. So first of all, upper bound was basically known since the 70s. We just did not know. So if you consider just a product rule for numerical integration, so you have some weights which are of product structure, you have a function where you have these Tij, so to say. So there's a product rule here based on some one-dimensional quadrature rule. Then what you get is the error of this algorithm of the product rule in the class CK upper bounded by the error of the one-dimensional times some factor which only depends on the weights. Okay, so what you need to find is you need to find a one-dimensional quadrature rule with a good bound on these weights here, which also has a good order of convergence. And yeah, that's well known. For these classes, there are good rules where a is equal to 1. If you consider periodic functions, you can really take just equidistant, just 1 over m. Okay, so that's basically all we need for the upper bound. This was essentially known. Our achievement was to prove the lower bound. And what happens in the lower bound is the following. What we need to do is, for a given point set in the unit cube, so for n points in the unit cube, we want to find one function which is 0 at every point but has a large integral. So why do we want that? Maybe I was a bit too fast here. Because that's also a formula, I think, already written by Bach-Wahloff. Worst case error here for approximation is just given by you take the infimum over all points, and then the supremum over all functions which have 0 information. Here is the infinity norm. If we would consider integration, and here would be the integral at this point. So you only need to find one function which has 0 information and has a large integral in the setting we are considering here. Okay, and the idea is rather simple. We take some indicator function which is just 0 close to every point in our point set, which is 1 otherwise. This function is clearly not smooth, but what we have is this function has a large integral. Okay, so if we know, we take the L1 norm here, so it's easy to compute that the integral of such a function is very close to 1, depending on n and d. I will show you how to choose the constant r here in a second. Okay. This is not a smooth function. What do we want? We want a smooth function, so let us just make it smooth. And what is the idea to make a function smooth? You can take convolution. So we have this function hr, which is 0 close to our points and 1 everywhere else. And now we take another indicator function, which is normalized here. And we just take a plus 1-fold convolution with our function here. So what this then gives is we have a function called fr, r is still an unknown parameter. We have a function fr, which is 0 at every point of our point set, but has the same integral than the original function hr. That's just simple rules of convolution. Okay, so this is basically all. What we then need to do is we need to find bounds on the derivatives, the infinity norm of the derivatives here. So what we obtain at the end is this function we just constructed as a norm that is bounded by something that only depends on the smoothness and on d and on the mysterious parameter r. So this is just an upper bound. And if we now choose r in the way we want to, that's precisely what happens here, then we get what we want. So we have a function in our class which is 0 close to every point of our point set and whose integral is very large. With very large, I mean close to 1. So since the function is bounded by 1, the supremum norm integral can be at most 1.
Excuse me, and why this function has 0 at every point? Because you can.
Okay, maybe. Yes. Maybe. So the original function, it would be a pleasure to draw it on the blackboard now, but I don't have a blackboard here. So you have a function which is 0 around all around every point.
Ah.
Right? And now you take a convolution with the function gr, which with a very bounded support. Very, and so if you now take the convolution with these functions, then of course that the area where the function is 0 gets smaller and smaller and smaller. But we put all the constants in a way such that these functions are still 0 precisely at the point.
I see. Thank you.
Yes, so at the end we have, that's I think a relatively easy construction here. So we have a function, large integral, still 0 at every point. So what we get by this is lower bound for these functions of this form. You already see d to the d, and it's simple volume arguments. There's really, I showed you basically the whole proof. There is no deep thing here. I think the idea of the convolution and getting the bounds on the derivatives was sometimes a bit technical, but not very deep. Okay. So now we just have to choose r. This was the radius of the initial function. So the radius where the function is 0 around every point in the beginning. And with this, we just get our lower bound that we wanted. So we get the number of function evaluations needed is lower bounded by this guy. Okay. So even if you take epsilon to be very close to 1, or say take it 1/2, right? No, we need at least, it must be smaller than 1/2. Take epsilon to be 1/2, and already we need something like d to the d over our function evaluations to achieve this error in the worst case. And basically, we could, for every point set you are using, we can write down a function that cannot be integrated correctly. Okay, yeah, here's a formula for the ck one, for this constant. That it's not so important now, I think. Okay, so what do we have for partial derivatives? We get this kind of result. Since I said I want to mention some open problems, let me come back for a second to the class of directional derivatives here. So we know this d divided by epsilon over d to the k, to the power d over k for partial derivatives. If we now take directional derivatives, we don't have a precise answer at the moment. We only know that we have the same upper bound because our upper bound was precisely like that. It's proven like that. Class is smaller, so the upper bound clearly also holds. As a lower bound, we only have the same with the square root of d here. And it's still an open problem, maybe not the most interesting one, but it's still an open problem in our thing, because we think we would learn a lot about general domains once we can solve that better. So let me state some open problems to see what is still open, although this class is studied now for quite a while. So first of all, what is the precise dependence on the dimension in this class of directional derivatives? That's the first. Some of my colleagues think that's a very important open problem. That's why I stated here. I did not work on that. I'm already satisfied with the results we have. Okay, so open problem number 2, I think, is much more interesting. So what the proof already showed, if you manage to follow my arguments, is that the lower bound basically holds for arbitrary sets. It was never needed the set has the cube. It was basically hold for every set. The only thing you need is that the volume clearly is about 1. The question is it true that the same upper bound we have holds for arbitrary domains? Because the upper bound, the proof of the upper bound really uses, this is the result of Haber, really use that you have a product rule, which means also your set must be a product set. So essentially a cube. That's still an open problem. And that's a different form, which is open problem 3, and considered by many other authors, also from different fields in mathematics. So the question here basically is the same as to ask if the asymptotic constant here, so you take the integration error in the class, domain dd, multiply it by the inverse of the order of convergence here, right? And the Lim sup. And if this asymptotic constant which exists, we know that the Lim sup exists, that Lim sup must exist clearly. So how does this depend on the domain? And it's a quite old conjecture, I think. Also, Hans Triebel was working on that quite a lot. If this Lim sup is essentially always a limit, or if the limit really exists, and if this guy does not depend on the domain, except volume. So there are many partial results. You could consider Lipschitz domains and smooth domains and all of this. But I think by now it's still, and I think that's an important open problem here. By the way, this is true for k equals to 1. So if you have smoothness 1, it's well known, and there is a precise formula for the limit, and this only depends on the volume. If you take k equals to 2 or larger k, as far as I know, we don't know.
Mario, excuse me.
Yeah.
A question. And what about the case when DD is not one domain, but 2 domains or 3 domains?
I don't know at the moment. But maybe I don't completely understand the question. So I think for many special domains, you just, you can compute that, but I'm not, okay.
So DD is a union of balls or of cubes, of small cubes.
I think this does not, so if you take the union of easy domains, then the question is also solved. I think that's not a problem. I think the main problem is if you now take the union of infinitely many of them.
Okay, thanks.
Yeah, so I think if the boundary is nice of your set, then there's no problem. I think there is a whole, maybe even a whole book about that of Hans Triebel. I would think. Okay. And there are some open problems, and now I turn to my favorite open problem. I was working on that for a while, but without any progress, by the way. And that's infinite smoothness. It's kind of surprising that if you ask the same question for infinitely smooth functions, then basically we don't know anything if you consider the d-dimensional case. So what do I mean? I take the class CD infinity, which is, it must be a double point here, sorry. So you take a function on the d-dimensional cube, and now all partial derivatives are bounded by 1. That's a very small class, and you even have bounded by 1. That's very, very smooth. These are analytic functions. Right? It would even be analytic if this guy decays something like beta factorial or so. But that's a very, very small class. But still, we don't know much. So note that this is often stated as a very easy problem to integrate functions from this class. Why? Because the worst case error in this class decays like n to the minus r for an arbitrary r. Okay? So you have infinite smoothness, so you even get an infinite order of convergence. So you know that the order of convergence is perfect. We don't know much about these constants. So what about high dimensions? So the best lower bound that is known here is only linear in the dimension. So you only have that number of function evaluations to integrate functions from this class goes like constant times d for some small epsilon. Our upper bounds we have, even if you don't care about the dependence on epsilon, are exponential in the dimension. So we don't know, is it exponential? Is it linear? We don't know. That's, I think, an important open question. I strongly conjecture the answer to this is yes. And the open problem is there a constant and some epsilon 0 such that the number of function evaluations needed to integrate functions from C infinity decays exponentially in D?
But Mario, do you have some description of this class? Like, you see, there are paper by Ulyanov about best approximation of Gevrey class. So it's, but then there is some bounds for derivatives, not one, but special one. And in your case, do you have any description of what is the function inside of this class?
What do you mean by what is the function? So we consider this class, so all functions that satisfy this.
Yeah, but it's not an independent condition. Some if you have bound for bigger derivatives, you can say a lot about first derivative and something. So in any case, it looks simple, but maybe it's sense to compare with Gevrey classes, some other classes of infinite differentiable functions.
Okay, yeah. So in our, we have two papers on that, as I told you, we have part 1 and part 2. And in part 2, we actually discuss these classes, these Gevrey classes. And there is, you have this parameter. If I would have known that this is interesting to this community, I would have stated these complicated results. But I usually think it's hard to understand. But there we really have, if this guy decays or increases or decays fast enough, I cannot remember completely, then we can prove some results, right?
Yeah.
But unfortunately, that's not, how to say it, that's the class where this is really decaying with D. So it's an even much smaller class than this. We don't have satisfying results.
Mario, here is also a kind of interesting question or effect here, that usually when we prove some results for finite smoothness, then this result, in a sense, does not depend on the domain. If we multiply, change the variables, like we shrink the domain or increase a little bit, like 2 times, it does not affect. But in your case, it's clearly affects because you need the derivative, the condition for all beta. So that means if you have something for cube 0, 1 to the d, then if you change this to the cube 0, 2 to the d, then it will be absolutely different story.
Yes, that's the main problem here. You have already seen it in the finite smoothness case. All these constants depend badly on the smoothness. So it's a factorial to the k or something. Yes, and cannot deduce anything from the finite smoothness case. This, unfortunately. But I think it's still a very interesting problem to see. So this very, very small class here, all bounded by 1, and we still don't know how this depends on the dimension.
But maybe it makes sense to look the paper by Ulyanov about approximation of Gevrey class. Maybe something.
I think we cited him. We had quite a look on these results.
Okay.
This was the motivation of Henryk Wozniakowski to include these results for these Gevrey classes, and it is 10 pages of ugly formulas. So I would.
Yeah, and the Ulyanov paper, it's also not very easy exponent of the. Yeah. Okay.
Yeah. Thank you very much. So. Yes, but let me say that there is some curiosity also here that if we now, instead of taking only the partial derivatives bounded by 1, if we now take all directional derivatives bounded by 1, which is an even smaller class, then we know that the answer to this open problem is no. And we cannot have an exponential dependence here. What we then get is some concept which is called weakly tractable, also introduced by Henryk Wozniakowski, I think in 94 or something, which means that it should be an epsilon. Sorry, it's some lattice error. These e's here are epsilon. So it basically means that the complexity does not increase exponentially, d or epsilon. Okay. That's also in our paper here, but as I said, the class for partial derivatives is larger, so that we have this does not mean that this is false. Okay, so now we had some open problems on integration, and we learned something about integration, so let us go to approximation. And to some extent interesting, we know a bit more in the approximation case. Okay, so what is known from the in the approximation case, depending on the dimension? So by a result of Nowak and Wozniakowski from 2009, we even know that for functions that are infinitely often differentiable, all partial derivatives are bounded by 1. Even in this very, very small class, you need at least 2 to the d/2 function evaluations for every epsilon. So if you want to reach an error of 0.999, doesn't matter, you need 2 to the d/2 function evaluations. And the function that you can consider here is just a linear function. It's just a clever construction, clever combination of some linear functions. And so I think it's a very interesting proof. Okay. So this is the case of infinite smoothness. And for finite smoothness, we can just use our results for integration. Why? Because approximation is a harder problem than integration. So the number of function evaluations needed for approximation is just lower bounded by the number we need for integration. And we just learned this is something like d/epsilon to the power d/k. So again, approximation is a very hard problem in high dimensions, as long as we consider these classes where all variables are equally important. I will not talk about cases where the variables are differently important. That's a completely different story. So I will stay with these, say, simple classes here. So the question now arises, we have this lower bound, when is approximation more difficult than integration? And so much more difficult. You might guess always, and the surprising answer is no. So let me start with the result of David Krieg, one of my favorite collaborators by now. He proved in 2019 that there is a case distinction, unfortunately. So for all k, this is constant ck, such that for all d and epsilon smaller than 1/2, you have, if k is even, see the familiar formula here is something with d/epsilon to the d/k. So 1/epsilon to the power d/k is the order of convergence here. Then you have some d/k divided by 2 here for even k. And for odd k, we do not know precisely at the moment. We only have the lower bound with this k/2, then upper bound with k plus 1/2 here. Still not completely clear, but although this is not the solution to the whole story here, we see that approximation is essentially harder in dimension if and only if k is larger or equal than 3. So for k equals 1, for k equals 2, so for k equals 2, they are just of the same difficulty, and for k equals 1, approximation is even simpler. And that's not simpler, but sorry. So of course they can only be of the same order, but for k equals 1 and k equals 2, there is no big difference between them. While for k larger than 3, approximation is really hard. Okay. So again, let us go to the case of directional derivatives, because here the story is again a little bit different. So for directional derivatives, we know precise order, we know the upper bound, and we know the lower bound. Other way. And here you just have this exponent k/2. So we know how this guy depends on epsilon and on d. It's e to the k/2 divided by epsilon to the power d/k. And from this result, compared with the integration again, we see that if we ask the question if approximation is essentially harder than integration, then the answer is yes, for k larger or equal to 3. The answer is just no for k equals 1. Both problems are of the same difficulty. And we still do not know precisely for k equal to 2. Okay. So let us give again some 3 open problems, which have the same titles, by the way. So first of all, what is the precise dependence for the complexity for approximation? In this case, the only open problem is for k. I was not working on this problem, by the way. The second one, which I again think is very important, is on arbitrary domains. It's the same as before. The lower bounds hold for arbitrary d, arbitrary sets dd. The upper bounds again use the structure of the cube. Again, we use product rules and all these things. So we do not know if the upper bounds, you see here, these upper bounds also hold for general domains. And I think this would be interesting. In the same way, you could ask for this asymptotic constants and so on for approximation. I think for approximation, this has a very long story. I never dig very deep into this things. Okay. And almost last open problem of my talk is again about infinite smoothness. So we get from the results of the last slides that for the approximation problem, you need something like d to the power d over 2 function evaluations. If you forget everything that depends on epsilon, you get an epsilon approximation. But for infinite smoothness, we only have 2 to the d written here so far, 2 to the d over 2. The question that one might ask is, do you also get something like d to the d, something like here, also in the case of infinite smoothness? Okay. Sorry. Okay. So this was everything about these simple classes CK, and let me add a small comment here. These tractability studies and all these things, how it depends on D, are very sensitive to the class of function you consider. Okay. So if you are going to study different classes, say Sobolev classes, where you have some integrability P and so on, then you must be very careful with the definition of the spaces, because changing some weights, changing the order of whatever, if you take bounds for the Fourier coefficients, for example, it's very essential what you take there, because the results might change drastically. So that's the reason why I think if you do some kind of these tractability studies, it should be about classes that are at least well accepted in the community. So you can find a lot of things going on there. I think at least for the classes CK, at some point we should know everything, because they are obviously defined classes and say simple. No one would define them very differently, I think. Okay. So in the last, say, 5 slides, I don't have much time about talking much about history here. And I already gave a talk 2 weeks ago about the setting. So let me shortly say something about L2 approximation. And that's a very short story here. Okay. So another setting instead of L infinity approximation is clearly L2 approximation. So we want to approximate an L2. And again, we want to use function values, and we want to take linear algorithms. So we compute worst case error in the class F. It's this guy. It's just the error of a linear algorithm using only function values. And then we take the infimum over all points for function evaluation and all, say, reconstruction functions, so however you want to call them. And this quantity here is known as the sampling numbers. I call it L2 sampling numbers because I'm using the L2 error. So that's the minimal error that can be achieved by linear algorithms that use n function values. And we can compare this guy, we want to compare this guy with the Gelfand width of the class F. The Gelfand width is just taking an arbitrary set of n linear measurements, so linear functionals on your class F, it's NF, combine these n informations by an arbitrary mapping phi. And that's everything that we could call an algorithm, right? It's not linear, it's just you have some fixed information, and you take some reconstruction. Yeah, I think the Gelfand widths are well known in this community. Okay. So you take something like the minimal error can be achieved with arbitrary information and arbitrary reconstruction algorithms. We'll just call them C and F. And keep in mind, that's L2 here. Okay. So in this case, and that was what I was talking about 2 weeks ago, we proved the result on these power of function values. So we proved the comparison result between the Gn of f and the Gelfand width. And this, although maybe it looks a bit complicated here, but okay, take an arbitrary class f, which must be in L2, so compactly embedded into L2, such that function evaluations make sense. So point evaluation is a continuous linear functional. Then we get this sampling numbers upper bounded by some infinite sum here over the Gelfand width. No matter which class you take, if you know the Gelfand width of your class, you can compute the sum here, and you get an upper bound for the sampling numbers. Here we have to take p strictly smaller than 2. Yeah. So I was a bit fast in preparing this slide. So there are also, I think, some recent survey results of Volodya, survey papers of Volodya, where the whole story is explained. So maybe one can have a look if one's interested in things like that. Okay, so and if now we want to deal with these quantities. Okay, so in the general setting, we have Gelfand width, which is the best we can do with arbitrary algorithms, with arbitrary information. And then we have the sampling numbers, which is the best we can do with linear algorithms based on function evaluations. And to come back to information complexity, we define these complexities, I call them NL2 here, which is the one minimal number of information, minimal number of function evaluations you need, such that the sampling numbers are smaller than epsilon. And here I call it NL2 and write all here because it all stands for all algorithms. It's just the minimal n such that the sampling widths are smaller than epsilon. Okay. And clearly this is the best we can do. And in practice, we usually only have this guy. I don't want to say much about, say, Olaf convergence or something. Let me just say 2 results on tractability. The result of David and myself in this setting shows, assuming that the best algorithm that is achievable at all, FD is an arbitrary class here, can be any sequence of function spaces, d-dimensional function spaces. Assuming you have this polynomially tractable setting with all information and all algorithms, you get a polynomial bound with p smaller than 2 here. So the dependence on epsilon is not allowed to be too drastic. Then you get the same also for function evaluations. So you don't lose anything. So you already know if you can approximate with some p. So here must be another log 1 over epsilon. I'm sorry, this was copy and paste error. So you lose a logarithmic factor only, but essentially the same.
Mario, how it could be that you need a lot of functional classes? I can take for one D specific D. If I have this theorem, I just can take all other classes empty. And so it should be a result for one specific D, the same kind of result.
Yes. So this is a result for every class F.
Yeah.
Here you don't need a sequence of or anything, clearly.
Yeah.
But you still might be interested in a setting like I had before, right? You just consider that the class is CKD, and you have D input parameters,
I see.
And now you want to know if I can do with function evaluations and everything, if this makes sense in high dimensions.
Mhm.
So it's essentially about this if the number of input parameters goes to infinity, what's going on then?
Mhm.
But yeah, of course, if you take some of the FT empty, I can even improve this result here.
Yeah.
So yeah, okay. So yeah, we have this. So what we get, I'm sorry, here is another log 1 over epsilon written here. I just forgot it. Sorry. Okay, so that's about the polynomial convergence. And what I think is even more, it's also very interesting, this exponential convergence setting that we already discussed a little bit earlier. So for infinite smoothness. So if you have a class of functions such that the number of function evaluations only depends logarithmically on 1 over epsilon. So there are many names for that. So it's just number of function evaluations is polynomial in D and only some polynomial in log 1 over epsilon. So some very fast decay, some very good order of convergence. And we get the same for function evaluations, same order in epsilon. The only thing we lose is some log D. Okay. So this, I don't have the time, I don't want to motivate it too much. This is a setting that appears relatively often when it comes to approximation of PDEs and so on. At least that's what people claim. And I never checked these applications. Often they just have settings where they have a very good decay, a very good order of convergence when they are allowed to have arbitrary information. And they just ask, what can we do in a practical sense? So what can we do with linear algorithms based on function evaluations? And this is the result we have here. And I think I had, anyhow, too many results and too many open problems. So thank you all for your attention.
Okay. Thank you, Mario. Questions? Any questions?
I want to make my one comment.
Please, Volodya.
Mario already mentioned that there is a recent survey, but that is not my survey. This is 4 authors survey: Boris Kashin, Yegor Kosov, Ira Limonova, and myself. And one can find this on archive. So yeah, indeed, it's a long survey and a lot of stuff in there. Thank you, Mario, for mentioning.
Mario, but may I ask a follow-up question? Long time ago, I was interested to application of some problem of numerical integration in finance. And then the classes, the natural classes are a little bit strange. For example, dimension is big, about 100, and you take polynomial of degree 2 of 100 variables, and then take absolute value. And
yeah,
it's interesting problem to find a good algorithm for integration such kind of function. Did you consider in this tractability, this, how to say, the classes which are important for finance and this one, for example?
So one point that the fooling, so the question maybe boils down to if the fooling function we constructed might also be in this class. And there the thing is, these functions are polynomials at the end.
No,
so piecewise polynomials, but they are
absolute
non-negative.
value of polynomials of second degree. So it's very easy to define, but it's the problem how to compute the integral.
Not piecewise polynomials. You really mean polynomials of degree 2?
Yeah.
And it's clear
absolute
that they have
value.
negative values. Otherwise, the absolute value makes no sense, right?
Yeah, of course.
No, so far not, no.
It's interesting class, and maybe it makes sense to consider specific this class because it's.
So my first guess would be yes,
finance.
you have the cursive dimension also for this class. This would just be my first guess.
Uh-huh.
But
But it will be interesting result that to show that even for absolute value of polynomial second degree, you have such a bad low estimate.
And you want to integrate these functions, right?
Yeah, exactly. And they really need this kind of estimate when they, how to say, modeling of options in finite.
Yes, yeah.
They need to compute the integral.
That's
But
very interesting point.
in general, let me make a remark in general. So that step, what Boris just mentioned, you take an absolute value, it is a very important step. Because for instance, if you consider like even functions from finite dimensional subspace, polynomials or whatever, integration of them, it's a problem, but not that big one. But now if you take absolute values, it changes the problem dramatically. So we know in some cases the answer because it will be this just discretization of L1 norm. So we know the answer in some cases, but it is a much more difficult problem.
Yes, but my guess would just be that making the absolute value makes the problem just harder.
Yeah.
I would guess so, for sure, yeah.
Yes, so any lower bound for integration that we have might just be applied also in this case.
Mm-hmm. Yeah, I guess so, yeah.
Yeah.
I'm sorry, I have a paper in 1988 about general setting. You have nonlinear operator, for example, you take absolute value. So function goes to absolute value. And if function belongs to n-dimensional subspace, problem is to approximate, to find estimate of widths in L2 of what happens after we take absolute value. And it's unsolved problem. It's interesting one.
Mm-hmm.
So
yeah, sure.
Nonlinear operators are not very suitable for widths. So
yeah, it's so the main problem is it's not. There is a formula here. If we have this formula here, right? And you might now guess if you take another problem, so take maybe L1 approximation or so, right? If this formula would still be correct for L1 approximation, then it's basically, then it's exactly what Volodya said, then it's just the same as the discretization problem in L1. But this is not true always. So because in L1 approximation, it cannot be true always.
I see.
But that's interesting. So I just put it into my. I don't have a pen here. What a shame. And okay, but so I put it in my smartphone. So now I have the information and we'll check the paper.
Okay. So what other questions? If not, thank you, Mario.